In this video, we will explore the steady-state response of series RC and series RLC circuits. The learning objectives for this video will be to show the steady-state response of RC and RLC circuits using sinusoidal sources. We'll also solve some sample problems pertaining to such circuits. So here is a circuit, an RC circuit with a sinusoidal source, and we won't derive the steady-state response for the circuit. We'll just show the result. So the result is that this is the steady-state response, where phi here is given by this expression. So again, the expression with the radical sign, we call it the impedance of the series RC circuit. Also, take note that the expression 1 over omega c, which is 1 over 2 pi fc, is what we call the capacitive reactance of the capacitor. And we have a new name for that. We have a new variable for that, which is x sub c. The unit there is also in ohms. So we can write the steady-state response in a more simpler manner. So that would be this. And again, we take note that this one is the amplitude of the steady-state response. So let's designate that as I sub m, which has this expression. We also plot the steady-state response of the RC circuit versus the sinusoidal source, and we observe that the response is actually leading the source voltage by an amount phi degrees. For the series RLC circuit, the response would be given by this one, and take note that this term here is called the reactance and also has a unit of ohms. So how does I behaves compared to the source E? So there are three scenarios. For example, if x sub L is greater than x sub C, we have a condition where I will lag the source by this much. When x sub L is greater than x sub C, the RLC circuit is said to be inductive in nature and behaves like a series RL. The second scenario is when x sub L is less than x sub C, so I there will lead E by this much. And when x sub L is less than x sub C, the circuit is said to be capacitive in nature and behaves like a series RC. And the third scenario is when x sub L is equals to x sub C. That gives us I there will be in phase with the source E, and the circuit is said to be purely resistive because x sub L and x sub C cancels each other. So again, the expression with a radical sign, we call that the impedance of the RLC circuit with a unit in ohms. We also have a quantity called admittance, which is just the reciprocal of the impedance Z. And the unit for that is called mho or Siemens. So I have summarized the formula for the series RL, RC, and RLC here. This is applicable for steady state responses. So you could refer to this table if it is needed. So this one is for RL, RC, and we have here RLC. So let's go over some problems. So here we have a series RC where the source is given as a cosine function, and we're asked to determine the impedance and the admittance of the circuit, the steady state current through the circuit, the voltage across the resistance and the capacitance, and whether this voltage is leading, lagging, or in phase with the steady state current. So here, first we compute for the impedance. So it's just a direct substitution. And after doing that, we can get the reciprocal to get Y or the admittance. And we could proceed to get the phase angle phi. So then we can use those values to determine our steady state current. So this is the formula here. So plugging the values, we will get this response. So just an additional note, our formula is expressed as a sine function. It's because we have a sine, or our source is expressed as a sine function as well. If our source is expressed as a cosine, we also need to change our I or our steady state formula to cosine. So after getting I, we could proceed to get the voltage across I sub the resistance R. So that would just be IR. So we could use I that we have already determined and simply multiply that by R to get the voltage across the resistance. And we notice that this voltage is actually in phase with I. So, just to emphasize, um, the voltage across a resistance is always in phase with the current that passes through it. Okay. Then we could go on to compute for the voltage across the capacitor. So that will be given as 1 over C integral of I dt plus any initial voltage uh, that is already in the capacitor before the switch is closed. Um, so plugging the values that we got or the formula that we have for the steady state current. So this is the steady state current. So we lock here dt here. So we didn't anymore include the initial voltage because at steady state this initial voltage will actually vanish over time. Okay, so evaluating this integral that will give us this result. And again, plugging in the values that we already got from the previous computation, that will give us these value for V sub C. And we notice that V sub C, with the presence of the sine function, we could conclude that V sub C is actually lagging uh, the current, or V sub C is lagging the current steady state current I by an amount of 90 degrees. So again, let me emphasize that whenever current passes through a capacitor, the voltage there will always be lagging the current through it. Also, an additional note, we could have computed V sub C by using this uh, formula. So this formula comes from Kirchhoff's voltage law. If we implement KVL around the series RL or series RLC or series RC circuit. Okay, so let's have a second example. Here we have a series RLC. It is connected to a source E where the given is an RMS value of the source equals to 100 volts and the frequency of that source. So the given source here is not a sinusoidal function, uh, but we know it is a sinusoidal function, but what is given is the RMS value of that source. So we're asked to determine the time domain expression of the voltage. So the voltage impressed, so that is the source, that is what we're looking for. So what is the time domain expression, or what is the sinusoidal function given the RMS value? Second is what is the effective value of the steady state current that will result from the series RLC, and whether this current is leading or lagging the applied voltage. Is the circuit inductive or capacitive in nature, and why? And last is if the frequency of the source can be varied, what frequency will give a maximum RMS value for the steady state response. Okay, first we need to understand that the source is a sinusoidal source, and if we're given the RMS value, we could always compute for the amplitude of the sinusoidal source, and that would be square root of 2 times the RMS value. And we could express the source in either a sine function or a cosine function. So here I use a sine function, so sine omega t or sine 2 pi f, so f is 60, and then t. So this will be our expression, sinusoidal expression for the voltage source of the RLC circuit. Then we compute for the inductive reactance, X sub L, and X sub C. So it's just direct substitution, and we get these values. We could also compute for the impedance, that now that we have the inductive and capacitive reactances, so that will give us this value. We could now compute for the angle phi. Since we have already the values for the inductive and capacitive reactances, so that will give us a negative result. That would mean that X sub L is less than X sub C. Uh, and that would mean that the circuit is a capacitive in nature. Then we proceed by computing or determining the steady state response. So we get this result here. So since the circuit is a capacitive in nature and behaves like a series RC, we will get a current that will lead compared to the sinusoidal source. So now that we have the steady state, we could compute its RMS value by dividing the amplitude by square root of 2, and that will give us this result. Note that the RMS value does not depend on the frequency of the source nor its phase angle. So as already mentioned, I will uh, lead E by 9.37 degrees because the circuit is capacitive in nature. That is, the capacitive reactance is greater than the inductive reactance of the series RLC. So for the last requirement, the question there is, what is the frequency of the source that will give us the maximum response? Or specifically, what we're trying to say is, what is omega of the source, or the f of the source, that will give us a maximum I sub m. Now, take note that I sub m is a function of the impedance Z, and since the impedance Z is also a function of X sub L and X sub C, and X sub L and X sub C is a function of the frequency, that means that I sub m will be affected by whatever the frequency of the source is. And we will get a maximum I sub m if we have a minimum Z. And the minimum Z will happen if we have X sub L equals X sub C. So what we need to do to answer this requirement is we simply equate X sub L equals X sub C. So that means that this one, omega L, must equals 1 over omega C. And that should give us what is the omega that will result into a minimum Z that will eventually give us a maximum response. So if we have omega, we can compute for the frequency, and that should give us this frequency here. So it is slightly above the original frequency of 60. And so what is the maximum I then, if this is the frequency? So that would give us uh, this result. So phi there would be 0 because X sub L and X sub C are equal, and therefore we will get this final result. And we notice that I there would be in phase with E for maximum steady state response. And we also notice that the circuit is resistive in nature because the effects of X sub L and X sub C cancels each other. This circuit condition is what we call a resonance condition. We will have some or we will have more of resonance when we go to frequency response um, in the next few weeks. So that's it for this video for series RC and series RLC. And on our next video, we will tackle the topic on phasor analysis. This topic is quite important because it simplifies how we determine the steady state responses of an AC circuit. As uh, you might have noticed, when we derive the response for the series RL, we use differential equations, and if the AC circuit is more complicated than that, that should give us a headache in terms of computing for the steady state if we are to use differential equation in solving the problem. So phasor analysis will greatly simplify the process.